Hey everybody, and welcome back to Math 104, Contemporary Mathematics. Today we're going to be looking at the end of section 12.2, our measures of central tendency, and 12.3, measures of dispersion. So, we looked at mean, median, and mode last time pretty directly as those three different measures, our average, our middle number, and our most common. And we looked at a whole bunch of different ways to display data, pie charts, line graphs, polygon graphs. And one of the last ones we discussed was the stem and leaf plot, or the stem and leaf display. All right. When you're using a stem and leaf, if you put everything into order, it's actually really helpful for finding things like your mean, your median, and your mode. But that's what this means here by rank, right? So we can calculate measures of central tendency from a stem and leaf display pretty directly if we just sort of take a look where the numbers all lie. So for instance, if we look at a stem and leaf display here, we've got our tens digit on the left-hand side and our ones on the right. It's pretty quick to find our mode, right? We look for whatever number occurs most often. I've got 3 2s here. I don't have 3 of anything else. These, of course, stand for 3 numbered 42, right? Tens digit, ones digit, there's our mode. For our median, well, I can count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 18, 19, 20, 21. Go to like the 11th number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There it is right in the middle. I also can kind of tell it's going to be straight directly in the middle quickly based on where all the numbers lay out. All right. If we were to go ahead and calculate our mean, of course, we'd still add them all up and divide by the number of elements. But the stem and leaf display is nice because we can use it to quickly identify some of those measures of central tendency. So when we talk about data, there are lots of different types of data sets, and two classifications we use are symmetric and non-symmetric. All right. So in a symmetric distribution, as we move out from a central point, the pattern frequencies is the same to the left and to the right, roughly speaking. It should be fairly close. If you think about symmetry in art, right? Two things that are the same, if you can cut them down a line and fold them onto each other and they match, that's symmetric. When we look for data points that are symmetric, can help us sometimes identify what's going on within a set. So here's a few different types of distributions that are symmetric. You have a uniform distribution here on the left. That's one where essentially every number is exactly the same. You'll notice the bar graph here, or the histogram, is a box, essentially, right? Same number being defined. You have a binomial distribution, one that is what we call normal, where it would start in the center and then move equally out from each side. And then there are other types of distributions, like bimodals, where you can essentially cut a line in the center and fold it on top of each other to give yourself a symmetric data distribution. And these are nice, another way to classify information and look at different data sets. There are lots of non-symmetric distributions, right? We have some that are skewed to the left, meaning that things are lower on the left, skewed to the right, meaning things are lower on the right or further out, and a bimodal distribution that's non-symmetric just isn't the same on both sides, right? So in that same concept of symmetry from art, if you can fold it onto itself over a line, you have a symmetric data distribution. If you don't, it's non-symmetric. All right, so that was really the end of the measures of central tendency. Let's talk about measures of dispersion. And measures of dispersion are a little different. So measures of central tendency talk about averages and centers. They're trying to find a representative that's roughly descriptive of most of the data. A measure of dispersion is more about how far away from those middles data is, how spread out it is, how dispersed it is, right? So we have a few objectives in this set. We're going to find the range of a data set. We're going to calculate the standard deviation of a data set. We'll interpret measures of dispersions and what those are. And then we'll calculate the coefficient of variation. So let's take a look at the range. Range is defined as the biggest value minus the smallest. It gives you an idea of the breadth of the values inside of a set, and it's pretty easy to calculate. So for instance, if I'm looking at two sets, I have set A and set B here. Take the highest, subtract the smallest. 13 minus 1 gives me a range of 12. Over here, my highest is 9 and the smallest is 5, giving me a range of 4. As a note, the mean and the median don't necessarily tell you how far apart those two values are. This is another way we can look at data sets. Like always, if we put the data in order, it does make lots of calculations easier. Not just the mode and the median, but also, in this case, the range. Easier to find the bottom and the top. Now, aside from range, we've also got variance. And variance is a little more complicated, but it's not too bad. First thing we do is we calculate the mean, right? We can see our x bar is sitting right here inside of the function. Then we're going to take the deviations from the mean of each individual value. So if I have 5 values, I'm going to take each one, call them x, and subtract the mean from them. Then each of those values I will square, add them all up, and then divide by n minus 1. In other words, if I have 5 items in my set, I'll divide by 5 minus 1, which is 4. Let's take a look at an example. So I've got this set of data here. It's got 5 elements. Let's go ahead and find its mean. Grab our handy dandy calculator. And we have our different elements, 1 and 2, 8, 11, and 13, for a total of 35, divided by the number of elements. There's our average, or x bar, right? So our average here is 7. Now to find the deviations, we'll take each of these values, again we're calling those x like in our formula, and we'll subtract the mean from them. So 1 minus 7 is negative 6, 2 minus 7 is negative 5, 8 minus 7 is 1, 11 minus 7 being 4, 13 minus 7 being 6, and then we can square those in order to find the top piece here. So 36. Reminder, of course, that negative times negative is positive. 1, 16, 36. And then to find our variance, the top piece here, we'll add all of these up. So 36 plus 25 plus 1 plus 16 plus 36 is a total of 114. And we'll divide that by the number of elements minus 1. We had 1, 2, 3, 4, 5 elements, so we'll divide by 4, which will give us a total of 'So our variance for this set would be 28.5. So again, find the average, subtract it from each data value, add them all up, and divide. Again, this tells you roughly the average of how far away something will be from the center of your elements overall. Now, let's go a little further, because that's not quite as awesome as standard deviation. Okay? Now, standard deviation is, generally speaking, one of the most useful measures of dispersion. Okay? It's based on deviations from the mean of the data, and it's also known as the variance squared. So if we take a look, the formula is actually pretty easy. We should recognize a large portion of it, right? So you'll notice the variance here is inside. Essentially, all we do to find the standard deviation is take the square root of that. So for instance, as an example, if we go back to the data set we were looking at a moment ago, and actually since we've done a whole bunch of work on this, let's actually reuse that, right? We already know what's going to go on our table and what our our variance was. Well, if our variance there is 28.5, because we've already calculated that, our standard deviation is equal to the square root of that, which in this case, square root of 28.5 5.33. Now, what is that really trying to tell me? Well, it means that on the average, roughly most of these digits are going to be around 5.3 away from the mean. And that actually kind of checks out relatively well, right? We remember that our mean here was 7, our x bar. Well, 7 plus 5.3 is almost 13, right? 11, if I look at that from distance-wise, we get a little under 6, with it being 5.33 if I pull it off, getting it closer. The 8 will be a little further away, but the 8's already close to the mean. The 2, if I were to add it, and the 1, if I were to add it again, are close to 7. So we're getting a rough idea of how far away from the average our values will be. And that's really the goal of standard deviation. So now, how do I interpret these measures of dispersion? Well, a main use of them is to compare the amounts of spread in a couple of different data sets and kind of look at what those mean. We infer then what those different data sets or those comparisons would be to understand what's going on in the system. So for instance, let's say I have 2 companies, A and B, and they're selling small packs of sugar for coffee. We all need our coffee. The mean and the standard deviation are given below, but what do those mean? Well, there are a couple of questions we could answer. We could answer and talk about which one's more consistent in providing more sugar in their packets. Well, if the average of company A's sugar per packet is 1.013 teaspoons, and the average for company B's packet is 1.007, well, the one who's giving us more of a higher average there is going to be giving us more sugar per packet. Company A is giving us more sugar for our coffee. Which one's filling its packs more consistently? Well, that's based on standard deviation here. If I deviate more from my average, like in company A, then there's a bigger difference between possible packets, whereas company B is a little bit closer, right? 0.0018 is closer to 0 than 0.0021. They're a little bit more consistent. So while they may be giving me a lower average, how much away from that average those packets are going to be is going to be smaller. It's going to be more consistent for my company. So if I'm opening a bagel shop, I can make the choice as to which one I would want to use. What your customers could be happier with. For me, I'd look for the consistent one. So we have something called Chebyshev's theorem. Chebyshev's theorem. For any set of numbers, regardless of how they are distributed, whether it's symmetric, whether it's non-symmetric, whether it's uniform, the fraction of them that lie within k standard deviations of their mean, where k is bigger than 1, is at least 1 minus 1 over k squared. Well, what does that mean? Well, everyone's used to seeing the normal distribution, right? And the normal distribution is just an example of one symmetric distribution. And in the normal distribution, just a rough sketch, right? We look at something where we have a nice bell curve, and we see that the mean is usually in the middle or is always in the middle. And we've probably seen this graph where you go through multiple standard deviations here and here, okay? And you say that, there's, say, roughly 34% in this first standard deviation part of the bell curve. Chebyshev's theorem is the one that allows you to actually calculate how many percentage points will be in each standard deviation regardless of the shape. So while it might be 34% here, it may be different for other distributions. So for instance, what's the minimum percentage points of the items in the data set that lie within 3 standard deviations of the mean? Well, we can take Chebyshev's theorem. So I can grab these. There's our little formula. Our standard deviations here is 3. So 1 minus 1 over k squared implies that we're going to plug in the 3. Means we're looking at 1 minus 1/9, which is 8/9. And if we take a look at our handy dandy calculator real quick, 8 divided by 9 is 0.88, or roughly 88.8%. So in those first 3 standard deviations, those first 3 sets of measure away from the center, you're going to find 88.8% of your values. And that doesn't matter whether it's normally distributed or not, that's for all data sets. So next up we have the coefficient of variation. And so this isn't really strictly a measure of dispersion, but what it is it's basically a measure of relative variability. In other words, how much something changes in comparison to something else, specifically here, the standard deviation to its mean. We have 2 formulas here, but they're essentially the same. So for our small s, again, we're talking about the sample's standard deviation, and the x bar, the sample's mean. With the sigma and the mu, it's the same type of value, just for the full population. Again, going back to our example in New York City, when we were surveying people for Coke versus Pepsi, if you survey everybody, I'd use the bottom one, population. If we just surveyed a few tens of thousands or a few hundred, we would use a sample, right? So how the heck do I find this? Well, it's actually pretty easy. a little long, but not too terrible. I have 2 data sets here, and I've done some of the work for you. So we've calculated the average of the first data set, we'll call it X sub A, to be 16.167, and then we found the mean or the X bar of set B to be 153.167. I've also gone ahead and had the standard deviation calculated, so 3.125 for set A and 25.294 for set B. So now we can take our formula, apply it, and take a look at our actual coefficient of variation. We're going to use S over X for this one. So as a little reminder over here, V is equal to S over X bar times 100. So if we take our calculator again, and pop it back in, for our sample A, we can take 3.125 divided by 16.167, 0.19329, so we're going to multiply that by 100, moving our decimal point over twice, which will give us 19 point, we'll go out 3 decimal places like we did above, 329. Note that I'm not rounding the 9 up because the 4 would keep it as a 9. Again, for sample B, we'll take our standard deviation, 25.294, and divide that by our average, 153.167. So we'll get 0.165, and again, we're going to go ahead and multiply that by 100, giving us a total of 16. We'll call it 514. Again, the 0 would not have us rounding up or rounding down what that coefficient of variance is. All right, so you might be saying, okay, we calculated it, but what the heck does that mean? Well, again, when we're looking at our coefficient of variation here, a higher one means that there's more variability, more distance from that mean, right? So in other words, sample A is going to be a little bit more spread out from its average than sample B is. So again, looking at those numbers, right? If I'm only 3 away from my average in the top number, based on size, I'm going to be a little bit closer on the average, a little further away, with these than I am from the bottom. Because even though this variation here is a little bit bigger, our numbers are much larger. It's a smaller percentage of distance, okay? It's a way of calculating, or at least looking at and comparing data of different sizes based solely on how far away they are from their average and not just their numbers specifically. All right, well, I look forward to seeing everybody on Tuesday. Just a quick reminder, we do have our exam on Tuesday. It will not include anything that's been gone through today in today's video, just up through through Tuesdays. If you have any questions, please don't hesitate to reach out via email. I'll do my best to get back to you quickly. And the homework should already be posted on Canvas. If you have any trouble, let me know. Otherwise, have a great weekend and see you soon.